Hello, I'm Seema and welcome to part 33 of the chapter Hydrocarbons. In this video, we are going to talk about the structure of the triple bond in alkynes. We have actually done this part, like we have done the structure of the triple bond when we did the chemical bonding and molecular structure. In that chapter, you have already done this. Yet, since we are doing alkynes, it is important to remember all of those basics and to understand the structure again. So let's start with it. Out of all the alkynes, the first member would be ethyne, because alkynes are defined as those hydrocarbons in which there is at least one carbon-carbon triple bond. Therefore, the lowest member should have at least two carbon atoms, and those two carbon atoms should share a triple bond between them. So ethyne is the molecule that is carbon triple bond carbon. It has two carbons, minimum number of carbon atoms, and there is a triple bond between the two carbon atoms. And besides this, it is attached to two other hydrogens, as we did in the previous video, that the general formula for alkynes is CnH2n minus 2. So if there are two carbons, N is 2, there are two carbons, Cn, N is 2, then what it will be the number of hydrogens? Hydrogens will be H2n. H is 2n minus 2. So 2 2s are 4, minus 2 is 2. So C2H2 is the formula of ethyne. C2H2, because it is the general formula is CnH2n minus 2 for alkynes. And N is 2 in the case of ethyne. It means it has two carbon atoms, so it will be C2H, 2 2s are 4 minus 2 will be 2, C2H2. Now what is important to remember or to understand its structure, let us go back to carbon and understand the tetravalency of carbon and the hybridization that we have studied about. Carbon has 6 electrons, it is the sixth element in the periodic table. It has 6 electrons in its shells. Now the shells or the orbitals may be described as 1s, 2s, according to Aufbau's principle, how the energy increases, and we arrange these orbitals according to their increasing energy. So the lowest energy is 1s, more than that is 2s, and 2px, 2py and 2pz have the same energy, so they've been put together and they are higher than 2s. So these 6 electrons can be arranged in these orbitals. So 1s orbital has 2 electrons, 2s orbital has 2 electrons, and 2px and 2py would have 1 electron each. Now, if you do not understand why am I putting 1 electron each, I would encourage you to go back to the basics, understand how electronic configuration is done. I've done a video on that also, and maybe a few videos I've done on that. So understand your electronic configurations also. But what I want to show, or why I want to revise this, is that this is the ground state of carbon, when carbon is not forming a bond with any other element, which usually does not happen, because if you look at this, in order to complete the octet, for any atom to be stable, it should have 8 electrons in its outermost shell. The first shell is 1, the number denotes the shell, and this is the second shell. The second shell has 4 orbitals. That is, one of them is a 2s orbital and 3 of them are p orbitals, px, py and pz. Every orbital can have 2 electrons, and that's the reason why it is said that the outermost shell, according to the octet rule, should have at least 8 electrons. So according to this, in the outermost shell there are 4 orbitals, and the number of electrons in the outermost shell are 1, 2, 3 and 4. There are only 4 electrons. So it needs 4 more electrons to complete its octet. But before doing that, before getting those 4 electrons or forming bonds in order to get those 4 electrons, the carbon atom gets ready to react. And when it gets ready to react, it is said to be in the excited state. And a little shifting occurs between the electrons. Why does this shifting occur? This shifting occurs in order to create a more symmetrical structure. Now, if you look here, the 2s seems to be heavy because it has 2 electrons. The 2px has 1 electron, py has 1 electron, and pz has nothing in it. So this is not even the weight, if you imagine the weight of electron to be minuscule, still at that level also the balance is not there. And not only the balance of weight, the balance of charges, that the electrons, negative electrons are so close together, or the negative electrons, they are all negative, they repel each other, they would prefer to remain as far as possible. So what happens? One of the electrons from the 2s orbitals jumps up to the 2py orbital. It's getting ready to react now. Although the energy of the 2py orbitals is more than the energy of the 2s orbitals, yet it gets excited and it runs up there getting ready to participate in bonding. So when one electron jumps up, what does the electronic configuration look like? So we call it the electronic configuration of carbon in the excited state. It has 2 electrons in the first shell. We are not concerned with the first shell, but the outermost shell is the second shell. So it has 2s, 1 electron in the 2s orbital, 1 electron in the 2px, 1 electron in the 2py, and 1 electron in the 2pz. Right? So now this is the excited state, that there is 1 electron in each orbital. When there is 1 electron in all the 4 orbitals, for bonding, covalent bonding to occur, every orbital can form a separate bond. So every orbital has 1 vacant space to form a bond in such a way that they have maximum distance from each other and they can form the bonds. And that is how, in the case of alkanes, I told you, the s orbital and all the 3p orbitals, they participate in bonding with separate atoms, and the distribution of energy takes place and the hybridization is called sp3, where 1s orbital and all the 3p orbitals participate, they redistribute their energies, they become symmetrical, and you get, even the s orbital is not different then. It seems to be it is of the same energy as the px, py and pz. There is a distribution of energies and the angles, a symmetrical structure is created. And that is why all the alkanes, they have tetrahedral, every carbon has tetrahedral angles. Then when one of the s orbitals and 2 of the p orbitals participate in hybridization and leave out one of the orbitals, p orbitals, the hybridization is known as the sp2. sp2 means 1 s orbital and 2 p orbitals are participating in hybridization. But in the case of alkynes, that is in the case of alkenes. So sp2 hybridization takes place. There is a double bond, that is the unhybridized orbital usually forms the pi bond, that is the multiple bonding is seen by unhybridized orbitals. Then in the case of alkynes, what happens? 1 s orbital and 1 p orbital hybridize. The other 2 p orbitals do not participate in hybridization. Why? Because they are not going to form single bonds. Since they are not going to form single bonds, they do not need to spread out. They are going to form multiple bonds. And in order to form multiple bonds, they don't need to spread out, they need to be more compact. Therefore, in the case of alkynes, the kind of hybridization we see is sp hybridization. There are only 2 orbitals which participate in hybridization, and these 2 orbitals will try to acquire maximum distance from each other. So imagine if you have 2 bonds, 2 orbitals, and they have to have maximum distance from each other. At what angle will they be maximum apart? At 180 degrees. Do you see this? At any angle, the caps are closer. If you take it down, the caps come closer. But it is only when they form a linear structure or a bond like this do they form, or an orbital which is linear. So that would be, it would form sp hybridized orbitals, 2 sp hybridized orbitals, but these 2 sp hybridized orbitals will be at 180 degrees from each other so as to have maximum distance, because that is the aim of hybridized orbitals. In in sp2, what had happened? The 1s and 2p orbitals, they acquired the 3 corners of a triangle, and therefore you got this structure in sp2 hybridization. But because this is the maximum distance, at any other angle the caps will come closer. It is only, they will be at maximum distance from each other when they are at an angle of 120 degrees away from each other. Therefore, the caps are occupying the 3 corners of an equilateral triangle. So now let us look at the structure that is formed of ethyne, keeping this in mind. In the case of ethyne, we know that both the carbons are sp hybridized. If we take into consideration the two sp hybridized orbitals, both the carbons have one sp hybridized orbital pointing towards each other. So if they are two sp hybridized orbitals, I have not made the smaller lobes. Both the sides will have smaller lobes. This is one orbital and I imagine this to be the second orbital, sp hybridized orbital. So one sp hybridized orbital, it overlaps sideways and it forms a carbon-carbon sigma bond. The first bond is formed by the hybridized orbital. The second sp hybridized orbital is absolutely opposite, that is at 180 degrees, is linear, I would say, is at 180 degrees from this hybridized orbital. So carbon has two sp hybrid orbitals, one on this side and one on the other side. The other carbon also has two sp hybrid orbitals, one on this side and one on this side. They are both linear. Oh, I'm unable to pull them in a linear fashion. You can just do it. So, okay. Yeah. Oh God, I hold it correctly in one hand and the other hand goes back. Okay. So they are linear. So on one side the overlapping takes place. Actually the overlapping means they merge with each other. Part of it overlaps and they merge the orbitals, because the orbital is just an imaginary space. So they overlap and they merge, and that is where the first bond is formed between the two carbon atoms. Where my hands are the carbon nuclei. The other ends, that is also the second sp hybrid orbital. That combines with a hydrogen atom. A hydrogen atom has only one s orbital, a single s orbital. So it overlaps with the s orbital of hydrogen and forms a sigma bond with the hydrogen. Similarly, on the other side also, the other hydrogen also had one sp hybrid orbital on that side. So that also overlaps with the hydrogen on the side. So there is one sigma bond between the two carbon atoms, one sigma bond between this carbon atom and the hydrogen next to it, and one sigma bond between this carbon atom and the hydrogen next to it. And the entire molecule appears to be linear. It is straight. Do you see? It's a straight molecule, 180 degree, 180 degree. It's forming a bond between two carbon atoms here, one with hydrogen here, one with hydrogen here, and it's just a straight line. So that is what happens. Now this is how you're imagining this whole thing. So this was the hybridized orbitals. What about the two unhybridized orbitals? What is their participation here? And why were they left unhybridized? Because the unhybridized orbitals were not supposed to participate in forming single sigma bonds. The two unhybridized orbitals will be forming multiple bonds between the two carbon atoms, which are known as the pi bonds. So we see these two carbons. Now we take the unhybridized orbitals. The px, so sorry, I should write py and pz. If this is y, let me write the x as z. Py and pz, because this is the px I have shown here is participating in hybridization. So py and pz are perpendicular to each other, the two orbitals, and they have two lobes. Each orbital, each orbital, whether it is hybridized or unhybridized, and it is a hybridization with p orbitals, it will have two lobes. In this case, the hybridized orbitals, the second lobe, this is one big lobe of the p part and a small lobe of the second, the s part. But I have not drawn the smaller lobe. But in this case, you just have p orbitals. So one lobe, one half of the dumbbell is up here and the other half of the dumbbell is down here. Right? So let me just bring the dumbbells. Alright, so I now have these dumbbells with me. Now look at this. The C, it has the 2py and the 2pz are like dumbbells. If this is the 2py, the 2pz is perpendicular to it. Now it is perpendicular. The 2pz in 2 dimensions we draw it like this. But actually it is perpendicular. If I had to show it, if you had to draw this that I'm showing you, and you could see both the lobes of this, the bond that is going behind the board and in front of the board. You would tilt it slightly and you would draw the structure like this, and that is what has been done here, which makes it look a little confusing. It doesn't look like a 90-degree, while actually the p orbitals are perpendicular to each other, right? They are absolutely perpendicular. So now the py and pz are perpendicular to each other, and they are also, I have made this separately, while actually you have to merge these two structures. These bonds are already made. Now there are these empty p or unhybridized p orbitals which are perpendicular to each other on both of these. One bond is formed in this axis, x-axis. So this becomes the y-axis and this becomes the z-axis. So you have the unhybridized orbitals along these two axes. Now, if this carbon has these two unhybridized orbitals, this carbon also has these two unhybridized orbitals. Now, when you have both of them have one hybridized orbital in this direction and the other hybridized orbital in this direction. Now imagine the hybridized orbital of this carbon in this direction and the hybridized orbital of this carbon in this direction. They can overlap sideways. You see, if they are parallel to each other, they can overlap sideways. They can be a merging that occurred. Again, I told you that the orbitals are imaginary spaces there, and imaginary spaces where the possibility of finding the electrons is maximum, more than 95% or 98%. More than, the possibility of finding the electrons of that orbital in that area. So it is an imaginary space. So these two lobes, they'll overlap each other sideways. And for the 2pz, if this is 2pz, then 2py is perpendicular. The two 2py orbitals are perpendicular like this, and they are also parallel. They will also overlap sideways. So when the 2py and the 2pz overlap sideways, they form two more bonds, which are known as the pi bonds. They result in the formation of, so I've shown you the red color shows that 2pz is straight like this. It overlaps with 2pz and 2pz here, which is straight here, and it forms a pi bond, while the 2py and 2py on this side, which are shown slanted but which are actually perpendicular, they overlap sideways and they form the other pi bond. So these two result in the formation of pi bonds. And here, the sigma bonds that were formed, they had a bond angle. I showed you that it is straight. So they had a bond angle of 180 degrees. It was linear. But these two orbitals, they are perpendicular to each other. So what is the bond angle between them? The bond angle between the pi bonds is 90 degrees. They are perpendicular to each other. So it is 90 degrees. So this is basically how you imagine alkyne or ethyne to be. Another thing, if you imagine now that there are these one orbital in the center is of course forming the sigma bond. The others are perpendicular to each other, and let us imagine that they are forming the bonds like this, the pi bonds. The upper lobe, lower lobe, upper lobe, lower lobe. So the bond appears to be, the whole molecule, it appears to be like a cylinder, but the molecule is straight. It is a cylindrical molecule. In the center there is a bond, and these lobes up down, which are at 90 degrees, they are surrounding the center. Imagine this center, the central line to be the sigma bonds, and these being the pi bonds. So they will all be forming a kind of a cylindrical structure. So it is a cylindrical molecule, it is a linear molecule, it is cylindric. If you really see this, as I showed you, if you imagine now the electron clouds will appear to form as if they are all overlapping and they are all together, and they form one long cylinder. So it is a cylindrical molecule. And the bond angles are 90 degrees. So let us now read what is there in the textbook about this. The textbook says, thus ethyne molecule consists of one carbon-carbon sigma bond. There is one carbon-carbon sigma bond. Two carbon-hydrogen sigma bonds. There are two carbon-hydrogen sigma bonds, one carbon-carbon sigma bond, and two carbon-carbon pi bonds. That is the number of bonds that the molecule of ethyne has. If you talk of the strength of the bonding, if we compare ethane to ethene and ethyne, if we compare these three and we compare this carbon-carbon single bond, carbon-carbon double bond in alkenes and carbon-carbon triple bond in alkynes, we find that a single bond is weaker. The double bond has a second bond. One bond is already there and then there is a second bond. So it has more, the strength is more. And if a third bond is also formed, the third bond with three bonds, that will be the strongest bond. So the strength of the bond can be measured in terms of the bond enthalpy. What is bond enthalpy? The amount of energy that is required to break completely two atoms which are bound together. So in the case of carbon-carbon triple bond, if you have to break all the three bonds in 1 mole of carbon-carbon triple bonds, the bond enthalpy is 823 kilojoules per mole. You need 823 kilojoules to break 1 mole of carbon-carbon triple bonds, but which is greater than carbon-carbon double bond. And what is the bond enthalpy of carbon-carbon double bond? It is 681 kilojoules per mole. If you had to break 1 mole of carbon-carbon double bonds, you will need 681 kilojoules of energy for breaking 1 mole of molecules. So, which is less than the triple bond. And if you had to break 1 mole of carbon-carbon single bonds as in alkanes, you will need 348 kilojoules of energy. So in order to, the bond enthalpy of triple bond or alkynes is the highest and the bond enthalpy of the alkanes is the least. You need maximum energy to break 3 bonds, you need a little less energy to break 2 bonds, and of course you need the least energy to break a single bond. So that gives you an idea of the bond enthalpy. Or you could say that the bond enthalpy of a triple bond is the highest. If you do not need to remember the exact values, you just need to know that the bond enthalpy of a triple bond will always be the highest, and the bond enthalpy of a double bond will be less than that, and that of a single bond will be the least. Then if you come to bond length, if 2 atoms are overlapping to form a sigma bond, it's the first overlap. So the bond length, they are comfortably away from each other. But when the second bond is formed, imagine, I always tell you, imagine bonds as friendships. So when the first bond is formed, this is the distance. You made a friend. And then you made a second bond, you grew closer, right? So the bond length decreases. As you get closer with your friend, the bond length decreases. And if there is a triple bond, you have even more things in common with each other. You get even closer. So the bond length really decreases. So we see that the bond length of a triple bond will be the least, will be the lowest, and the bond length of a single bond will be the highest, because when the friendship is not so strong, it's just one single bond. You met the person once or twice, and therefore it is a single, the friendship is not as close. So carbon-carbon triple bond, the bond length is 120 picometers, which is the lowest. For carbon-carbon double bond, it is less than carbon-carbon double bond, which is 133 picometers, greater than that, and which is less than carbon-carbon single bond, which is 154 picometers. 154 picometers is the length or bond length between carbon-carbon single bonds, which is the highest. So what do you conclude from all this? That the electron cloud between 2 carbon atoms is cylindrically symmetrical. I showed you that if you imagine the electron cloud now, you will imagine it to be a cylinder, and it seems to be a symmetrical cylinder around the basic, if you imagine this basic central hole to be the sigma bond and the basic skeleton of the molecule, this whole electron cloud, it forms a cylindrical structure. So the electron cloud between 2 carbon atoms is cylindrically symmetrical about the internuclear axis. What is the internuclear axis? The line that joins the 2 nuclei of the 2 carbon atoms and the hydrogens. This is the axis, internuclear. All the nuclei are in one line. So this forms the internuclear axis. And the electron cloud is symmetrical between the 2 carbon atoms, is cylindrically symmetrical about the internuclear axis. Therefore, ethyne is a linear molecule. Wherever you have sp hybridization. Now, mostly you'd be asked questions where you'd be asked the structure of a molecule, if it is sp hybridized, if it is sp3 hybridized or sp2 hybridized. So you can tell whenever the hybridization is sp3, the structure is tetrahedral. Whenever the hybridization is sp2, the structure is triangular planar. And whenever the hybridization is sp, the molecule, that particular part of the molecule is linear. Right? According to hybridization, the molecule would be linear. So this was about the structure of the triple bond, taking the example of ethyne. With this, I'll wind up this video. If you wish to watch other videos of this chapter, please click the link that appears on top of your video. And if you found this video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos on chemistry. Thank you for watching, and bye-bye for now.